I'm, of course, very pleased to be here, and I want to thank for the invitation to talk about some of the work we have been doing actually for quite a long time. And it's sort of unusual for me that the two speakers before me actually spoke on a subject that was similar to what I'm going to talk. So it's a very pleasant and surprising experience. We have tried to divide the things a little bit among us. So I'm going to talk a lot about, not a lot, but some partly of our experimental work, which I think is quite important. So the talk today, I'm going to say a few words about cosmic rays and climate, but you already heard a lot about that. Few of the definitions, the empirical evidence, we also seen some of that, but it never hurts to hear some of these things once again. But then I will talk about our experimental efforts and our quest to try to understand what type of mechanism, what is the microphysical mechanism? And the final part will be in order to understand whether there is a real effect on the atmosphere. Is it something that we can see? What you see here is a schematic of our solar system. You have here the sun, and you have this huge area which we call the heliosphere, and it's mainly the sun's magnetic field, or you can say it's the solar wind that fills up this enormous space. And what is happening, or what is important in this context, is that we have these cosmic rays that are produced in our galaxy, mainly from these stars that are exploding, that accelerate particles to very high energy. Then this part of space here, the heliosphere, is working as a shield against the cosmic rays. So the amount of cosmic rays that you have where you have the Earth is around half of what you have outside the heliosphere. And again, as we've seen in the previous talks, if you have a change in solar activity, you are actually changing this shield against the cosmic rays. And typically, when we have this change in solar activity, we change the amount of cosmic rays on the order of 10%. So we're going to talk about 10% changes of that order. When we talk about the millions of years, which Nihat was talking about, where we go through spiral arms, we are talking about changes on hundreds of percent, so it's a much larger effect. But I will not dwell on that. Now, what happens when the cosmic rays enters into the atmosphere? What you see here is a simulation. This is in fact Chicago, and one of the Great Lakes. We go up in about 15 kilometers, and you have a very energetic proton coming in, and then you see this shower structure where one particle produces an enormous amount of secondary particles. In this case, with the energy that this particle is having, it's probably on the order of 1 billion secondary particles. But in any case, you get these showers, and they are ionizing the atmosphere, and these changes the chemistry of the atmosphere, because the ion, when you have ion chemistry, and of course you also get these nuclear reactions, so that's how you get the cosmogenic isotopes. We already heard about carbon-14 is produced by this method, and that's why we know that we have a signal that going very far back in time, so we know actually solar activity going far back. So here you see these stalagmites, and this was just one example. It illustrates what we have known for quite a while, that there is a connection between solar activity and climate. I think it's as close as you can get to a fact that changes in solar activity is changing the Earth's climate. I mean, when I started this in the mid-90s, I went into this field. At that time, I was told by most people that there were no effects of solar activity, and the effects that people have been claiming were just spurious. They were not real. But I think over the years, it has become, completely clear that this is not the case. There is really a connection. So there is really a scientific problem that needs to be understood. Why is there these correlations? So that is more or less how I got into this work. I had noticed that there were these correlations, and the speculation was, what could be the connection? At that time, some people were speculating it was solar irradiance, but it looked as if solar irradiance would be too small to explain the kind of changes that we see in climate. And I think now, today, we have better understanding of the changes in solar irradiance, and it is believed that solar irradiance is probably too small to explain what we are seeing. So the idea was that we need something to amplify the effect of changes in solar activity. And the idea was, at that time, perhaps it could be clouds. Because if you make a systematic change in the cloud cover, then you are changing the amount of energy that reaches the Earth's surface. So somehow you would expect that changes in solar activity could change the Earth's cloud cover. That would be a very nice way of amplifying this effect. And when we had this idea, what we had to do was, of course, try to look at data. And what I'm showing you here is one of the updated graphs that we started with. It is showing the change in the cosmic rays, which is the red curve. And then you have the blue curve, which is actually low cloud cover. When we did the first work, this data set here was only updated until 1990. Subsequently, we saw that the curve was actually following the cosmic rays quite well. But then something happened in 1994. There was a problem here, and we identified a problem in the calibration of the curve. And that's why I put in this calibration, because we actually recalibrated, or at least attempted to recalibrate the data. I mean, the problem is that it's really difficult to measure cloud cover, even from satellites, and it's a very, very difficult task to do it over a long period of time, where you have to have, many instruments have to be stable in the space environment for a long period. So it is actually quite difficult. But nonetheless, it indicates that there is a correlation, and of course the correlation could be spurious. We can't be exactly sure that there's a physical link between the two. But we have to try to, it opens the question, what would be the mechanism? So we were sort of at this point, the empirical evidence was quite clear that there is a connection, or it looks as if there's a connection between cosmic rays and climate. Each time we had a change in cosmic rays, we see a change in climate. And if the link is between cosmic rays and clouds, then of course the obvious question, what is the microphysical mechanism? Now, when we came out with this figure here, people were saying to us that they couldn't believe it, that this idea probably would be wrong because there was no known physical mechanism that should link ionization to the formation of clouds. Nothing is known about it. And then the attitude from many people was that, other scientists saying that it is something that we cannot take seriously. But we actually took it seriously, and we tried to see if we could, investigate it further. And actually, that has to do with doing experiments to see if we could find such a mechanism. And in order to understand what kind of experiments you want to do, then you have to understand how clouds are formed. And what you see here is an attempt to demonstrate schematically how clouds are formed. So you want to create a cloud droplet. And a cloud droplet is mainly consists of water, but in order to make this condensation of water vapor, you have to have cloud condensation nuclei in the atmosphere. And no matter I mean, even on a clear day, the air is actually full of small aerosol particles. They are present everywhere. But it turns out that if you go over the oceans, where it seems to have very pristine conditions, then it is known that you actually, directly from gases in the atmosphere, you start getting nucleation of new particles, where you have small molecular clusters that stick together, and then they subsequently can grow by condensing more vapors, and then they become cloud condensation nuclei. It turns out that this mechanism of producing the small clusters has not been very well understood. In fact, it has not been understood at all. So there was really a big question here, and that's why it was something that we immediately started focusing at. So the idea that we had was that ions produced by cosmic rays could help stabilize these small molecular clusters. And if you then have more cosmic rays coming in, you produce more of these small aerosols, you get more cloud condensation nuclei. And if you have more cloud condensation nuclei, you actually change the properties of the clouds. You get more cloud droplets, so the cloud appear wider. A second effect is that the cloud droplets actually become smaller, so you get less precipitation, and that means that clouds live longer, and when they live longer, it looks from the satellites as if it's more cloudy, and it is more cloudy because it's more cloudy more of the time. So here is the problem that we focus at experimentally. So what we did, and this was an experiment that was done between 2002 and 2006, so it's already fairly old. We had a reaction chamber here. It's about 2 by 2 meters. And then we have various instruments where we can measure what is going on in the chamber. And the basic idea is to take some air in this chamber and have it as clean as, for instance, over the Pacific, and then put in some trace gases. And these trace gases I'm talking about is sulfur dioxide, it's ozone, and it's water vapor. So we put everything in this chamber and keep it constant: temperature, pressure, the concentrations, and the only thing we change is the ionization inside the chamber. And this is actually the experimental setup where you see the chamber here, but it's not particularly interesting, but it gives you an idea what type or how the experiment looked like. This is the result. That down here we have the ionization produced by the gamma rays. So here we have a high ionization. I think the ionization here corresponds to maybe 10 kilometers or something like that. And then down to the surface level. I mean, the ionization increases as you go up in the atmosphere because you have more cosmic rays or secondary particles up there. And then the second axis, that is the production of these small aerosols. And you see a very nice correlation between the two. I should say that these were quite difficult measurements to make. There's a lot of it's very difficult to keep these conditions. This is 300 parts per trillion. So it's a very, very low concentrations. And I think still today, this type of experiment this is the lowest form of, lowest concentration of CO2 done still. Okay, so it indicates that there is a mechanism, and I will now show you some of the other experiments we have been doing since that period. We did an experiment actually in a mine in England where we went down 1.1 kilometer, and the reason we did that was because we wanted to avoid completely the ionization from the cosmic rays. Because the cosmic rays are so energetic, you actually need 1.1 kilometer of rock in order to get rid of the cosmic rays. So the cosmic rays are gone, but what is not gone away is the ionization from radioactive gases. So you also have to prevent these coming in. So this is the laboratory you see here, and this is the this is like a lead coffin where we put in the experiment. I'll show you just in a minute here. So here you have a very thick layer of lead and a very thick layer of copper. And that is actually to avoid the radiation altogether from the environment. And with that in place, we could get the ion density down to about 1 ion per cubic centimeter. And the idea, of course, to see, is the ionization taking place if we don't have ions present? And we cannot do that at the surface. Just to show you some of the experiments, this is the chamber that we were using. And here you have, this is some experiment over a few days. And here we have a certain level of production of aerosols. If we then put in the ionization, you see immediately we get a very nice increase in the number of particles. And if we switch off the radiation, we go back to the same level. So it just illustrates that we can actually reproduce our experiments quite well. And I think this is also showing this reproduction. This is taken in this bulby 1 kilometer below the surface. And here we have, what we do is that we actually put in UV light into the chamber, just a short burst, and that produces a lot of aerosols. And then we shut off the light, and then the particles decay because they move out to the surface of the chamber. And we could do that, and then we can increase the radiation a little bit, and you can see that how nicely we are able to reproduce. So we have very nice and stable conditions. So one of the things we see is, here we see the nucleation rate as we increase the ionization. We see that as we increase the ionization in the chamber, we get more and more production of these small aerosols. But we also see, as we go to zero, that we don't get zero formation of aerosols. So this photo-induced nucleation, where you have your UV light producing sulfuric acid, is also taking place at the same time. Maybe unsurprisingly, but at least we could test it. But there is a very interesting result that we got, because we are measuring at a certain level of sulfuric acid concentration. When we shine the UV light on into the chamber, we get a certain concentration of sulfuric acid. And then we can measure for different sulfuric acid concentrations the amount of ion-induced nucleation. I mean, how big a part of what is going on is caused by ion-induced nucleation. And it turns out that as we go down in concentration, we see that the effect is increasing. So the ion-induced nucleation takes over. And I should say that over the oceans, we have to go all the way down here in order to get these concentrations. And you can imagine that this curve might continue. And we would like to see how far it continues. But it indicates that the ionization becomes more and more important. And under the atmospheric conditions, it will be quite important. We did another thing right after the bulby experiment, and that was to take our equipment to an accelerator in Aarhus, where we, instead of using gamma rays, we then use electrons, because people have been saying that maybe particles will have a different effect on what you're doing compared to gamma rays, because that's a different way of doing things. It turns out that when we do this type of experiments, here again, this is the ionization that we get from shooting the beam through the chamber, and this is the formation rate of particles at 4 nanometers. It turns out that if we compare that with our gamma rays, we get the same results. So one conclusion is that it doesn't matter whether you use particles or gamma rays. maybe it's not very surprising, but it's a good indication that you can actually do these experiments without a particle accelerator, and it makes it much more cheap to do it because an accelerator is very expensive compared to radioactive sources that we used. Now, then a few months ago, this very large collaboration, which is called CLOUD at CERN in 2011, they came out with their results. Here you see the chamber. It's actually 27 cubic meters. We were working with 8 cubic meters, so it's a very large chamber. You have the beam coming in through here. And the number of people you see is not representative of how many there actually are. I think there are between 60 and 70 people working on this experiment. But they actually showed that when you, they got results which actually supported our results very nicely, in the sense that as the intensity of the beam increased, so the ionization increased, they also saw a large increase in the production of small aerosol particles. Now we get to the last part of my talk, and that has to do with the question whether it works in the real atmosphere. Because when we came out with the experimental results, people were saying, okay, maybe there is there is a physical mechanism. But when you put that physical mechanism into the real atmosphere, it will drown in all the other mechanisms that are present in the atmosphere. So if you produce a few aerosols more, it wouldn't matter, because it will be completely drowned in all the other, for instance, cloud condensation nuclei present in the atmosphere. So that was sort of the idea, and I think still most people think like that. But it turns out we can actually answer this question, and this is what we have been trying to do. So what we have done is to use these effects from the sun. What you see here is a change in the, you see a solar activity, and the direct light is blocked by a screen. But you see these explosions, and if these explosions where the plasma is thrown out, if that hits the Earth, it can make the cosmic rays drop quite significantly. Here you see an attempt to visualize the event that happened in 2003, where you have this ejection of plasma. This is the Earth, this is the sun, and you see these two clouds coming out here. And I think it's it's a matter of a day or two before it reaches the Earth. Then you have a drop in the cosmic rays. Here you see one example. This is July 1982. This is the 13th of July, 14th, 15th, 16th, and so on. So these are individual days. And then you see this sudden decrease in the cosmic rays happening over actually hours. And you can see that is actually like a big natural experiment with the whole Earth. That all of a sudden you have an effect where the cosmic rays drops by the order of 15%. It's almost the same as you have over a solar cycle. And then the question is, does something happen to the Earth's cloud cover? And this was the type of results that we were getting. If we take this one, this is day 0. This is 20 days after the event, and day 0 is the day where you have the minimum in the cosmic rays. And then you have 15 days before. So you have these events happening at the sun, and you get a dip, and then you get a recovery. But if you then look, for instance, at the liquid water content of the oceans, you see that following this event, you also get a dip in the liquid water content. And it is interesting. First of all, there is a delay, and also the amplitude is on the order of 6%. A 6% change in the in the water content in the clouds is actually a huge effect, because the change in ionization is on the order of 10%. So it suggests that a large fraction of clouds are affected by ionization. This is the implication. Now, we used different data sets with different instruments, and actually not even the same, because they were up in different periods. So we see it also in completely independent data set that there is an effect in the cloud cover. But equally interesting, we also see it in the aerosols. This is based on the aerosol network. It's called AeroNet. And we see a dip here following these events on the sun. So we actually see the whole chain from solar activity to cosmic rays to aerosols and to effects on clouds. Okay? So what I'm showing you here is various, I mean, this is liquid content and this is cloud fraction. But you would imagine that if you are changing the number of aerosols, you are changing the microphysics of the clouds. So it would be appropriate to try to look at individual cloud parameters. And there is this data set from Moody's, and where we can do this study, and we look at different cloud parameters. I'm not going to go too much into it, but for instance, you would expect that the optical thickness, that is how bright, how wide the cloud is, would be affected. So you have fewer cosmic rays coming in, you have fewer cloud condensation nuclei, and you get a change in the brightness of the clouds. In the cloud fraction, you also see a very nice thing in the liquid water pass. That is how much water there is. We also see this effect. We see marginally an effect in the effective radius that actually increases, which is exactly what we would expect. We don't see anything in the cloud condensation nuclei, but when we calculate, we find out that this signal has to be in the noise of this system. So this is one thing we don't see, but we actually see it in the aerosol network, where we see this effect on the aerosol. So the last thing I want to show you is that when you have these Phobos decreases, they are not alike. They are all different. What you have here is the energy of the cosmic rays, and then the number of cosmic rays coming into the, this is the number of cosmic rays on the top of the atmosphere. So when you have a Phobos decrease, you get a screening against the cosmic rays. That means that all of a sudden you have fewer cosmic rays. So the spectrum is sort of dipping down, but it's not such that two Phobos decreases are alike. They are actually quite different. So some of them will be, strong, and some of them will be weaker. And we did a huge effort in order to characterize these events. We used all neutron monitors available. I think it's on the order of 130. In order to characterize this change here. And when we know this change, we can rank the different Phobos decreases. We can say which ones are strong with respect to changes in ionization and which ones are weak. And doing that, we can actually try to see if there's a relation between the strength and the effect we see in the clouds. So here we have the strengths of the Phobos decreases. And you see the stronger the Phobos decrease, the larger effect you get. So there is a very nice linear correlation. If you look here, this is the effective radius. It is actually increasing also. I should say that with this type of data, you are really fighting with the noise or meteorological noise that is present. So it is a constant battle of finding a signal which is buried within. And you have to do it in a reasonable way. But when we do that, we actually see very clearly these signals. So let me just, for the I think it's the last slide, this one, say why there is a delay in the, why we have the dip in the cosmic rays and then there are a few days before the effect is seen. Now, we expect that, the idea is that the cosmic rays are producing or help to stabilize these small aerosols, which then subsequently can grow to some certain size. But in order to affect clouds, they have to be, in this size range. So you can imagine that you are producing or this is helping producing a lot of small aerosols. Then this effect on the sun is happening, and all of a sudden you get a generation of particles where there are fewer. There are not so many particles because the sun has, taken away the cosmic rays, so we are producing fewer. So you have a generation of particles that are small, but they take some time to grow, and after a few days, then they start affecting the clouds. That is the basic idea. So let me conclude. We have this very strong empirical evidence that each time we have a change in cosmic rays, it looks as if we have a change in climate. And one of the evidence which is sort of independent is this evidence on the long time scales, that is these millions of years. Suggestion is that clouds might be quite important. It is certainly that an effect needs to be amplified. Something has to amplify it, and clouds seems to be a very good candidate for doing that. I think that over the years, we have found more things that indicate that we might be on the right track than things that goes really against it. There have been many new studies, I think, that sort of suggest that this could be right. But it involves, of course, these ions and this aerosol formation. And it is really interesting that it suggests that a large fraction of clouds is actually produced by ions, or ions are very important for the formation of clouds. And the final thing I will say is that it's interesting that we actually see the effect now from, almost hours to years, to the solar cycle, to thousands of years. And then we have the jump to the millions of years, so and even billions of years. We see an effect. It holds the potential, very potentially that it can explain, a lot of the things that we have been seeing with respect to climate variability. Thank you.